All right. I'm going to talk a little now about the divergence and curl of B. Look at the divergence and curl for me. This is section 5.2. Hey, Lily, how's it going? How's it going, Curl? Okay. Divergence and curl of B. And 5.3.1 actually is for straight line currents, which is what we've been dealing with because there's the easiest. We're crawling before we walk, before we run. Now, let's look at this. Let's just say what? What if we take for a straight line current, for a wire with current. Now, this is in 302, I would say wire. In 212, I'd say, war. If I was teaching high school again, I was like, in a war. No, I wouldn't, but it's a joke. If you work on a job site, you'd get it. This is B.dl. And if you do that B.dl, basically what we're going to do, since this is all around it, it's integrating over a circle, so we're going to take some point, got this wire running here. Here's our current, this point here, say our point of interest, and we're going to go all the way around at the same distance here, we're going to call S. We're going to go all the way around it, so we're going to basically take that and go around 360 degrees. See if I can do the robot. That's the way we're going to do it, okay? Topher, Ashby, you go to the clubs, do the robot. Gets all the chicks, man. You can do it. Or as they would say in the movies, you can do it. Okay, so there's enough of that. All right, so we know B for a long straight wire. We said that is mu naught I, and this is a long straight wire. Remember, infinitely long wire. We know that's equal to 2 pi S. S doesn't change over the integral, so it's really just going to be over that circle dl. We're going to go all the way around on that. Well, all the way around on that, if the radius of that is S, all the way around is at that point, we're going to look at what B.dl is. We'll just take whatever the B is, dot it with this. It's just going to be, because at all times, remember, all times B, I'll say, to do this, B is the B field goes around, so B is parallel to DL at all spots. So that dot product is just multiplying them together. It's the angle between them is 0. So theta equals 0 degrees. So the cosine of 0 is just 1. That's the reason I was able to get rid of that dot product there. Okay? Now that's just going to be 2 pi times the radius because that's all the way around. Again, it's circumference. Integrating circumference. So that's mu naught I 2 pi S times 2 pi S. Cancels. And we get mu naught I is what B.dl equals. So that's what we get. Now, if we look at this, they say, what if you change the circle, change your S? Is it change what this is? Well, it's still equal to that. Why? Because the field, conceptually, when you get out further, you may go longer around, but your B field is weaker. Weaker by the same proportional amount. So it doesn't matter how small or how big your radius is, B.dl, the B field strength dotted with that circumference around equals the same thing. As the circumference gets bigger with the radius increase, the magnitude of B decreases, and they counteract each other. That's why it's constant. And that's what they're trying to show there in figure 527. So that's for one wire. For a bundle of wires, we would just take mu naught, the current enclosed by the basically your point of interest. Enclosed by this circle here, and the radius of that. As long as they're inside that circle we're going to integrate, it would be this. It would be just, we're just taking into account all of them. It's just summative. It's superposition. They just add up. Okay. Now, we did just do something with, say, a current. A bunch of wires going through something. We have a bunch of current going through, like I said, across a point. We said, but this current enclosed, we can write that in terms of the current density, J. J dot dA. Where current density, this is over how much current's going past a point. If you dot it with dA, with that area there, you can get how much current goes past. You get how much current goes past. Well, if that's true, then I can put this right there. So mu naught J dot dA. Well, does that tell us anything? Not really there. Maybe later. But this B dot dL, I can write this, though, in terms using the Stokes theorem. And Stokes theorem was way back in chapter 1. And Stokes theorem, let me go back and find it if I can. It was under integral calculus. Here it is. Stokes theorem. Dun, dun, dun. It basically says, if you look right there, that integral V dot dL, I can make that into a cross product over an area. Ha ha ha. So rather than looking at this, I'm going to cross it with everything in that area there, that area vector. Remember that area vector is perpendicular to that round circle there. All right, so if I do that, this dot product now can be a cross. And so I'll get this is over the integral of del cross B dot, and that's this whole thing, dot dA equals mu naught the integral J dot dA vector. Okay. But I got dAs on both sides. Sounds like I'm in court. I got dAs on both sides of me. I must have really did something bad. No. Jeremy, that's you on the other hand. No, I'm kidding. But I got DAs on both sides. There's differential areas, not district attorneys. All right? But if I got the same thing on both sides in algebra, we can just cancel it. And same thing you can do here. That's an integral, that's an integral. Well, geez, why don't I cancel these? Because it's the same thing, and I'm just left with, and I'll put it right here, I'm left with del cross B equals mu naught J. Well, J, remember, is current density, and this is the curl of the magnetic field. This is the curl of the magnetic field. And we derived it from just that. What about that it gives us? Now, this is only for long straight wires. But it's also valid for, we'll say, other configurations. But this was just the easiest way to show it. And that goes into 5.3.2, which I'm looking at and going, no. And what I'm going to say is, it can show, of course, that this is good for all of them. Where are you going, Lily? Where are you going, girl? You going someplace? Okay, see if you can find Chloe. See if you can find the kitty. Okay? All right. This is Ampere's law. This is Ampere's law. Now what's notice, this is differential form. I've got differentials here, derivatives. This is differential form of Ampere's law. No integrals here. And we won't put it in integral form. But this is the differential form of it. So let's go back to put it back to here and put it in integral form. I'll say for integral form, let's go back to here. Del cross B dot dA vector equaling mu naught J dot dA vector. And if we do this, of course, this works back to being, this here we said is B dot dL, and this here we said is mu naught I. And this is the current enclosed by that point up there, by that current. This is the current enclosed. And what we're going to say, current enclosed by, and that loop there, we're going to call it an Amperian loop. An Amperian loop. Now, as you're starting to notice, there's a symmetry involved here. There's a symmetry. With electrostatics, you had Coulomb's law, but from Coulomb's law, what did you derive? Gauss's law. And you said, Gauss's law, much easier to get electric fields than Coulomb's law. Ugh, cavemen say ugh. All right. With magnetostatics, cavemen say ugh. Magnetostatics. Cavemen didn't understand magnetostatics. Electrostatics, yes. Magnetostatics, too hard. So we're going to be better than cavemen. All right. You start out with BO sub art, but when you do some looking at it, mathematically, you can get Ampere's law. That's a little bit easier to calculate than using BO sub art law, as you saw. So let's do a simple example and demonstrate. This came off pretty good earlier. Let's see if it does here. Woohoo! Only going to take this part off. By the way, if you got one of these at home, this one leaves much less residue than this one. So this is all Integrates had, so I had to pull them from her. All right, so let's do that magnetic field of a long, straight wire, a distance S from the wire. Now we know the answer. I know we know the answer. This is just showing how easy it is. And then we'll start here in class on Monday doing the next one. We just take that equation, do it like Gauss's law. Do it like Gauss's law. And so, B dot dl, for I enclosed. Well, we're still using this picture. This is now the current enclosed. Here's S. So all the current that's enclosed, we just got one wire this time. Wire. One wire, and it goes through that Amperian loop. This is your Amperian loop. You do your integral around your Amperian loop. If you remember in Gauss's law, we did it over that surface area, remember? E dot dA. All right. So if we look at this, we know at this point B is constant. B is constant because it's the same distance away everywhere along the Amperian loop. We're going to integrate over the Amperian loop. Just like we integrated over the Gaussian surface we had. We did Gauss's law. So the B is constant. I enclosed. Well, I enclosed is just current, so I'm just going to just use I because that's just that for that one wire. Okay. And if we do that, it's mu naught. Well, we know that it's just all the way around. Now, you can go formally and do the calculus if you want. We're at a point now, you guys are juniors and seniors. That's just 2 pi r. That's easy peasy, lemon squeezies. All right? And in this case, not r, it's just going to be s since that's the radius of it. Equals mu over I. Now, did you like that derivation or the one I did at the very beginning of the first video in this set I put up? I think you probably like this way of doing it better. It's like Gauss's law compared to Coulomb's law. It's a lot easier to find electric fields. The integration's a lot simpler. It makes more sense, honestly, to figure it out for many people. This is how you do Ampere's law. It's basically the analog, as you notice, to Gauss's law. Coulomb's law analog is the Biot-Savart law. Okay. For electrostatics to magnetostatics. Is there one that would work for both? One law that work for both? Maybe. We ain't there yet, I don't think. I don't know about it. Maybe there is. That's how you do it. I'll do the next example, and we'll do a little bit more on class on Monday. But I wanted to get a good start on this. And, yeah, I think that's pretty good. All right, thank you.